So I think we can start. So in the last lecture, we started talking about polynomial chaos expansion, but we really, to be very honest, did not discuss anything about polynomial chaos expansion. Instead, we were discussing or we were reviewing some concepts from functional analysis, right? And that is essentially what we did. So what are the things that we discussed in functional analysis? Can you remind me? What was the first thing we discussed? Square integrable function in vector space, which basically tells you that it's a collection of function in vector space where the second moment is finite. Then after that we talked about inner product space, and it's a space where the inner product you can calculate, and it depends on the probability measure. It's not a dot product as in the usual Rn space, but rather it depends on the PDF fxx, right? After that we talked about the norm space. After that we talked about the distance metric. Then Cauchy's sequence, which is a sequence that looks like it has converged, but it is not necessary that it will converge. In some spaces, Cauchy's sequence do converge. For example, if Cauchy's sequence do converge in the metric space, we call it a complete metric space. If Cauchy's sequence converge in the norm space, we call it the Banach space, and if it converges in the inner product space, we call it the Hilbert space. And essentially Hilbert space is what we are interested in, right? Hilbert space is what we are interested in, and that is where everything will happen. So in the last lecture we talked about Hilbert space. We discussed Hilbert space, right? How do you define it? It's a square integrable space where the inner product holds and it is complete. So Hilbert space fundamentally, this is basically an inner product space that is complete, right? And complete means, what does complete means? Cauchy's sequence indicate convergence. It's not that it is like converging, it is converging. So Cauchy's sequence means convergence. So when Cauchy's sequence means convergence, we call it complete. Be it the complete inner product space, which we are calling Hilbert space, complete norm space, which we are calling the Banach space, or the complete metric space, which we are calling the complete metric space, right? So in that sense, how do you define it? I mean, mathematically, how will you write it? So first you will write a space, let's call it F, and F is defined as function. So F is a vector space where each point represents a function. Okay, so it's so all the functions that represents that are there in this space, corresponding to which or which maps from, let's say, a k dimensional space to a real space, such that expectation with respect to F, G square is less than infinite. This is the square integrable space. This is the definition of square integrable space. And what is F here? PDF of x. So this space is defined by a random variable x having a probability measure, which is PDF fxx, right? So this And then from this square integrable function space, if you take two functions, let's call them g and h, then the inner product is defined as g and h. Then the inner product, the generalized inner product, is defined as, remind me, fxx dx integration. So integration of gx hx fxx dx. So this is basically your inner product space, and if this inner product space is complete, you call it the Hilbert space. Okay, you call it the Hilbert space. Now remind me, why is Hilbert space important? We discussed it last time. Can you remind me, why do we care about Hilbert space? All the property of Rn space, which is basically a vector that we know, holds for the Hilbert space. So whatever we know for vectors will hold here. For example, we know normalization for a vector, so there will be a normalization. Same thing you can use here on functions. We know orthogonalization, Gram-Schmidt orthogonalization. The same thing can be used in the Hilbert space. Whatever you know in the vector space or the Rn space, that is, as we call it, holds for the Hilbert space. So that means if you can show that a function belongs to Hilbert space, then done. You don't need to show all of those things. You can directly use those properties, and we will be using those properties. Okay, so that is why Hilbert space is very, very important. And that is why in most papers you will see journal articles that everything is in the Hilbert space. We work in the Hilbert space in most cases. In some cases we work in the Banach space also, but Hilbert space is more generic. Banach space is a subset of Hilbert space. You can think of it like that, because inner product space, from there inner product you go to the norm space, and a complete inner product space is the Hilbert space, a complete norm space is the Banach space. So in that case, but not all property that holds in Hilbert space need be true. Need not be true in the Banach space. Okay, but anyways, we only care about Hilbert space, at least for the polynomial chaos expansion that we are going to discuss somewhat today. It will not will not be able to complete it today, but we will start discussing it, right? Okay, so now we are in the Hilbert space, which is similar to Rn space. In Rn space, if there is a point on that Rn space, how do you represent it? That's a vector, but how do you represent a vector? Basis vectors. E1, E2, E3, Ij, K, whatever you call it, and you know that any point on the vector space or Rn space can be represented using the basis vectors multiplied by the coefficients. We know that, and we have been using it since long. So if that is the property of vector space, equivalent properties would be there for the Hilbert space. So in Hilbert space, what will happen? That we need to define something which is like an orthonormal basis or orthogonal basis, and then any function in the Hilbert space can be represented as linear combination of the orthonormal or orthogonal basis, and that is what is polynomial chaos expansion is. That is what we will be using for reliability analysis, and that can also be used for uncertainty propagation. Okay, that is what polynomial chaos expansion is, that you represent a function using orthogonal polynomials. Why is it called chaos? I don't know. The name was coined some 100 years ago. I think 1930, if I'm not wrong. Weiner coined the name chaos, but it's actually basically orthonormal polynomials and representing a function using orthogonal polynomials in the Hilbert space. That's what it is. Okay, so we'll talk about it more in more details, but first let us bring the basis function or the orthogonal basis into picture, right? So orthogonal basis in Hilbert space, right? So what is orthogonal basis? It's a set of basis function belonging to F, obviously, which is the space, right, which satisfies certain criteria. So it's a set of basis function, or I need not use the term basis function, a set of function. It will be a basis function, but let's call it a set of functions. Now phi is generally what is used for polynomial chaos expansion, but I will not use phi because phi I have used for standard normal distribution. So I will use psi. Okay. A set of functions psi 1, psi 2, and it can go up to infinite, all of which belongs to this space, which satisfies the following properties. And now what are the properties? The inner product will be equal to 0 if and only if I is not equal to j. Okay. So this is equal to psi I, psi j is equal to 0 for all I not equal to j, right? And then what will happen if I equal to j? Not 1. If it is 1, then that's a very special type of orthogonal polynomial. We call it the orthonormal polynomial because it is normalized. In a generic orthogonal polynomial, it will be some positive quantity. So let's call it ai square. Square for all I equal to j. Right? A slight change in notation I will do because ultimately I will be using the orthonormal one, so that I will use psi. So for orthogonal I am using psi tilde. Okay. Because psi I am reserving for orthonormal polynomials because that is what I will use. Okay. Now are orthogonal polynomials unique? Given a distribution, obviously. Without giving, it's a function of distribution, by the way, because this inner product that you are seeing will have fxx sitting inside it, but they are not unique. This you multiply it by a number, it will be still be orthogonal polynomial, same as orthogonal vectors. Orthogonal vectors are also not unique. So therefore, orthogonal polynomials are also not unique. If one of the polynomial is 1 minus x, 2 minus 2x will also be a orthogonal polynomial, okay, in that sense. And therefore, orthonormal polynomial is generally what we use because orthonormal polynomials are unique because you are bringing one additional constraint into picture, which is the normalization constraint, which essentially enforces that this will be equal to 1. The second equation will be 1. Okay. Special type of orthogonal, again I have written basis here, you should write polynomial. We will use it at this will act as a basis vector, that is correct. So basis is not wrong, but right now we are talking about polynomials, right? And polynomial is more generic. Basis means it has a specific function. Polynomials might have other functionalities also. Basis is one of them. So better to write functions. So a special type of orthogonal polynomial, in PCE we use it as a basis, is orthonormal polynomials. Okay. A special type of orthogonal polynomials is the orthonormal polynomials, and for orthonormal polynomials the second equation will become 1. It will be normalized.
Interchangeably using functions and polynomials.
Oh, functions means in this case polynomial function. Polynomial function. So these are all orthogonal polynomial functions, to be more specific. Okay, there can be, you are right, there can be functions which are not polynomials and still be orthogonal, sine, cos, and all those things, right? Yes, in this case, when I'm writing orthogonal function, I mean orthogonal polynomial functions. I mean, or okay, so that is what I mean. You are right. Thank you. Okay, a special type of orthogonal polynomial is orthonormal polynomials, which is where the properties, the first property remain as it is, psi I, psi j is equal to 0 for all I not equal to j, and the second one changes, psi I, psi j is equal to 1 for all I equal to j, and combining it I can write it as a Kronecker delta function. We are aware of that. So which is basically psi I, psi j is equal to my Kronecker delta, right? So by combining these two, I can write it as the Kronecker delta, correct? Okay. Some more properties before I go ahead. So here I have only represented from 1 to infinite, right? There is also, and we will go by the notion that psi 1 is the orthogonal polynomial of order 1. Psi 2 is a orthogonal polynomial of order 2. So then there should be one psi 0 also, which is the orthogonal polynomial of order 0, right? And that, so the constant one will denote as psi 0, okay? The constant one will denote as psi 0, okay? Now these properties in statistical point of view, you can also write it as, these are equivalently written as, see, expectation of psi I is equal to 0 for I equal to 1 to whatever, okay? But expectation of psi 0 is equal to 1. Psi 0 is a constant, and that constant for orthonormal polynomial will always be 1. That is how the normalization will be imposed. And expectation, and by the way, all these expectations are with respect to f or fx, whatever you call it, which is the PDF x of that space, right? So probability measure. So expectation of psi I, psi j is equal to delta ij, okay? Psi I, psi j will come out to be delta ij. What is expectation of psi I, psi j? Psi j? It is the inner product, right? And inner product is equal to delta ij. We have already seen that, okay? The other two are additional thing that you are getting. That expectation of psi I is equal to 0, I equal to 1 to whatever you take it, and expectation of psi 0 is equal to 1. Okay, so these are the properties of orthonormal polynomials, and this property ensures that you get a unique orthonormal polynomial. You will see it. We will derive some orthonormal polynomial today, and that time we will see it, that how we can use these properties to derive orthonormal polynomial for a given measure, and that measure will take the easiest one, uniform, but you can also imagine using Gaussian and all those things, okay? I said that's a property. Without that, you will not be able to uniquely find the orthonormal polynomials, because you need to normalize it. So that means if you have to find out n constants, you need n equations. You will not have n equations without that, right? So that's how you get it. These are properties of orthonormal polynomial. Like how do you get that inner product to be equal to delta ij? That's a property of orthogonal polynomial. You are defining that orthogonal polynomial is polynomial that satisfies that. You are not saying that this will always be, now you show that, okay, if this is satisfied, then it's an orthogonal polynomial. That's what you are defining orthogonal polynomial as. So this is how you are defining the orthonormal polynomials. That this properties needs to be satisfied for a polynomial to be classified as orthonormal polynomial, right? Psi 0 is a constant. Yeah, so that's why it will be 1, right? Yeah. Not even orthonormal, that's a property of PDF. That's a property of PDF what you are saying. But this is a property of orthonormal polynomial. If it is orthogonal, this expectation of psi 0 should be equal to some A, which is the constant you will get. That need not be, for orthogonal it need not be 1. It will be some constant, right? So in that sense. Okay. One more thing someone asked, right, that the first property, can you derive the first property, I mean some intuition from the second equation? Psi I, psi j, the inner product is equal to 0 if I not equal to j. So expectation of psi I, can I not write it as expectation of psi 0, which is 1, and psi I, and that is equal to, understood what I'm saying? That's what is happening there. Okay, but it's a property. Okay, this is a property of orthonormal polynomial. Okay. Any doubt? No, psi I, psi j will every time be 0 because you have the orthonormality property applies on 2 bases at a time. So psi I, psi j, 2 bases are already there. You cannot add anything more. Right, so 2 are already there. So there is nothing to add. Exactly. So 2, right? Okay.
Just to confirm, the first property will want to for orthogonal as well as orthonormal.
Yes, yes. The second one is only for orthogonal. That is the one additional equation that you get. We need one equation, right? We know that if there are n in vectors, we can find out n minus 1 uniquely, and depends on the what you assume the nth one. So here we are assuming that to be 1, and everything else follows from there. Orthogonals are not unique. Unique. Exactly. Exactly. You can rotate again. You can only rotate it only one direction. So there it's actually not unique in the sense you get plus and minus. You will not get anything else. You cannot rotate it. It will not remain orthonormal. What you can do is you can change the direction of the. Like if it's x, minus x is also orthonormal. So that you can do. It is in probability space. When you rotate it, the probability measure will not rotate. So it will lose the symmetry and all those things. When you are rotating it, it's not its inner product, you are thinking it in a Rn space. But here the probability is sitting there. Orthonormal, for Rn space, orthonormal is unique. Even there, orthonormal is unique. You cannot rotate it. Eigenvalues, eigenvectors, can you rotate it? So then eigenvectors give you the orthogonal, right? And if you normalize it, that's what you get the orthonormal, right? Eigenvectors are the orthogonal polynomials. Eigenvectors are unique to a certain extent, and if you normalize it, it is unique. If you normalize the eigenvectors, it's unique. So that's why n minus 1 I was saying, that's from eigenvector, right? Same thing. Yeah. Expectation of, we don't take expectation of inner product. If you take expectation of inner product, it will be constant. Expectation of inner product is inner product, because inner product will give you a constant. Expectation of a constant will give you a correct. No, so look at it like this. It will not work what you are saying. So expectation of psi I, psi j you are trying to do, right? So now, first expectation of inner product of psi I, psi j. So first let us do inner product of psi I, psi j. That will either be 0 or 1. Expectation of 0 is 0, expectation of 1 is 1. You get that, right? Now what you are saying is that you want to reverse the expectation and this I mean, the two expectation you want to reverse, right? I have to check, but seems like the property will hold, but that is of no use, I think. I mean, we will. That is the inner product. That's the inner product.
So you are doing expectation of psi I value.
Yeah.
Inner product.
No, expectation of psi I psi, not inner product. I'm not. Do you see the angle bracket there? So there is no. It's a product of expectation. What is psi I psi j? I just defined it, right, somewhere. This was g and h. Is it not expectation of gx multiplied by hx? The inner product. Look. So that's what I've written, right? The last expression. So it's not, I understand your confusion now that you are talking about expectation. It's not expectation of inner product. Expectation of the product of psi I psi j. That is by definition inner product. Is the inner product. Is the inner product. Okay.
ये तो प्रॉपर्टी हमने assume करी है ना.
कौन सा प्रॉपर्टी?
Last
प्रॉपर्टी वहां से आ रहा है ना, from the second line.
just आ गया.
That is the definition. I mean, psi inner product. The definition of inner product is this equation. Substitute g with psi I, h with psi j. You will get the expression, right? Same thing, nothing else. Okay. Okay. Let us proceed. There is one more property of Rn space that we are going to use here, and that is what I said at the beginning of the lecture, that any point on the Rn space can be represented as linear combination of the orthonormal basis ei, ej, ek, right? Same thing we will do here. So a function, okay, now f is for PDF, g and h, so let's use g. A function g in the Hilbert space can be represented as linear combination of the basis function, which is the orthogonal polynomial or orthonormal polynomial. I will rewrite orthonormal, but it can be orthogonal as well. There is no problem with that. Space can be represented as linear combinations of I'm writing orthonormal, but it can be orthogonal also. Normal polynomials, which means it is acting as a basis. So now the term basis comes into picture. This means that the orthonormal polynomials are now acting as a basis, and it satisfies the orthogonality property of basis functions anyways. Which means this g, I'll write it as summation I equal to 0 to infinite ci psi I, right? Now in the Rn space you have n basis function, right? In the Hilbert space you have infinite number of bases, and that's the generalization of vector to function. I mean, you can imagine as a function as an infinite dimensional vector. If you imagine it like that, then this anyways comes, but that's an intuition, more of an intuition, okay? Which we'll also use when we talk about Gaussian process later. That we'll talk about it as an infinite dimensional Gaussian distribution. But anyways, so this is the same property that we use for vector. Same property we bring here, where ci is my coefficients that I want to find out. Psi I is my orthonormal basis. Now the basis term I can use, and this expression is nothing but expansion in orthogonal or orthonormal polynomials. But this expression is what is known as the polynomial chaos expansion. Okay, so this is known as the polynomial chaos expansion. So yeah, so right now, I mean, previously I said, right, that I don't know where the name came from. I still don't know where the name came from, the chaos term at least, but it just struck me that, as I said, it was by, I think, Weiner in 1930 is the one who coined this term, chaos. And I think at that time, chaos was I mean, chaotic systems are inherently uncertain that because there is a small change, it becomes uncertain because it diverts. So in chaotic systems, if you change the initial condition a little bit, the output is widely different. So it's as if it's uncertain. And so uncertainty, you can relate it with chaos like that. And because the basis function depends on the PDFs, which is basically talking about uncertainty. So maybe that is where the name chaos came from. I don't know. I'm just speculating. Orthogonality, but that need not be, that has nothing to do with chaos theory. But yeah. Yeah. So from there, but why did they use? That's the question. That's what I don't know. That's what I'm trying to speculate. That why did they use the term chaos? I do not know. But that's a speculation that came to my mind. Okay. That they used to relate because chaos was discovered much later by Lorentz. So at that time, chaos was similar to uncertain. You don't know. Now there is PDF, so uncertain, so chaos. If it is chaos, then polynomial chaos. I mean, that's a speculation. Okay, my speculation that I came up with just now. Okay. Otherwise, I do not know why the name chaos is there. But polynomial is quite obvious. Expansion is quite obvious. But for practical purpose, you can think of it like a orthogonal polynomial expansion. You can think of it like that. Okay. Okay. Now, what is the norm of this G? If I write it G like that, what is the norm of the G? How do you find out norm of a function? Inner product of the function with itself. Norm of vector is inner product of the vector with itself, and then square root, obviously, that I am not writing. Norm of G is square root of inner product of G comma G. Norm of vector A is inner product of A dot A and then square root. Same thing, right? So norm of G will be equal to, norm of G square actually will be equal to summation I equal to 0 to infinite Ci square. And this is known as the Parseval's formula. This is known as the Parseval's formula. And let us derive it. It's a two-line derivation. So let's find out the norm of G square, which we know is G comma G, right? Now write G using that expansion. Summation I equal to 0 to infinite Ci psi I comma summation, I am using J here to separate the two, Cj psi j, right? And then this is equal to Ci summation over I summation over j, the limit I am not writing, Ci Cj norm of psi I psi j, linear property, right? Same thing, integration and summation, you can interchange them, and the psi I psi j will give you delta ij. So it will only survive when I is equal to j. So you will end up with Ci square. Okay. And again, this is nothing new. For vector, this property already holds, right? So this is known as the Parseval's formula. Now, let's go back and think of it from a surrogate modeling perspective, because ultimately that's what we want to do. If we want to use this to develop a surrogate model for a function G, what is unknown? The C's are unknown. Psi will be known because you will know the PDF of the input variables. So from there you can construct psi, right? C is what is unknown. The coefficients are unknown. How will you find out the coefficients? This I discussed last time, but let me repeat that. One option is you will formulate a regression problem, and from there you can think of finding out Ci or C's by solving the least square regression. And that is one way of doing it. We do it in the non-intrusive way of doing things. That is known as the non-intrusive polynomial chaos expansion, which we will discuss separately, but we can do it there. There is another way of doing it, which is also non-intrusive or can be intrusive. Both ways it can be used depending on how you are using it. And that is by taking inner product of this G with psi j. So if I take inner product of G with size j, I will get Cj. Again, the same property from vector. If I have vector A, and if I do a dot of A with I hat, I get A1 along I hat. Same thing. Right? I'll repeat it once more. For a vector A, represented as A I cap, A1 I cap plus A2 J cap, let's take 2D. If I do A dot I cap, I'll get that A1. And we know that. And dot product is equivalent to inner product. So here if I take dot inner product of this G, which is summation Ci psi I with psi j, I will recover my Cj, right? So one way of finding Cj is as follows. And I'm saying one way because, as I mentioned, there are other ways also. So Cj is basically your inner product of G and psi j. Now G, if you write, it is summation I equal to 0 to infinite Ci psi I comma psi j, right? Again the same thing will happen. So summation over I equal to 0 to infinite Ci psi I psi j, and now the only thing that will remain is when I is equal to j, that will give you 1, everything else will give you 0 in the summation. So this is basically equal to Cj, right? So this is basically projecting the function onto its basis function, right? Same thing you do for vector, and this is one way of finding out the unknown coefficient, right? This is one way of finding out the unknown coefficient. But in all of this, there are two things that are most important to think about it. One of that we have somewhat discussed, and I will give some example now. The other thing we'll discuss in the next lecture beginning. The first thing is orthogonal or orthonormal polynomial, and how to construct them. Given a distribution fx, how can I find out the orthonormal polynomial? That is one of the basic and most important thing for using this. The second important thing is that this inner product, right? Will it always, will we always be able to evaluate it analytically? There will be cases where you will not be able to evaluate it analytically, and you will see it when I go to the orthonormal polynomial. So we need efficient way, accurate way of evaluating this inner product, and that is achieved by using quadrature rule, which I'll talk about some of the quadrature rule that are used. The basic ones you know, for example, midpoint rule you probably know, which is with a single point square. Trapezoidal rule you know, Gauss quadrature you know, Newton codes you probably know, I'm not sure. And the Newton code is based on which Gauss quadrature was developed. And there is one more, I am forgetting the name, but that is the one that is used here. So these 5 at least, no, that I will not forget. This is something I have not heard, right? Okay. Gauss quadrature obviously is the most efficient one, but we don't use it because it's not nested, and you will see it next time. That name I'm forgetting, but that uses Fourier basis. You transform it into sine cos domain and then do it. Okay, so I'll discuss it next lecture. Today we are the remaining lecture, 10 minutes or whatever it is remaining, we will focus on orthonormal polynomials. Okay. orthonormal polynomials. Okay. So I already talked about how to find orthonormal polynomial, right? By using those expectation formula. So let us do one thing. Let us take one case, a case of uniform random variable, and let us try to find only the first two orthonormal polynomials, psi 0 and psi 1, and that will give us idea how to do it. Okay. So in general, generally the orthonormal polynomial, let's call it psi n. What is n here? The order. It is represented as summation I equal to 0 to n a0 x to the power I, ai x to the power I, sorry, let me correct it. ai x to the power I. This is the obvious way of writing it. And now the objective will now be to find out these a's such that the orthonormality properties are satisfied. So the objective is now finding psi is equivalent to finding ai's by using the properties discussed before, and that is basically the orthonormal properties, right? So as I said, we will take a simple case, uniform distribution from 0 to 1, okay, and we'll try to find out psi 0 and psi 1, that's all. Okay, so special case to illustrate basically special. So I have x which comes from a uniform distribution in 0 to 1. Okay, I am interested in psi 0 and psi 1. So what will be my psi 0? I know it's a constant, so let's call it, assume it to be a0. What will be my psi 1? Not a0. These two a will not be same. So b0 plus b1x, just to ensure that they are right. So I have how many conditions? 3 unknowns, a0, b0, b1. This is, so I will need 3 equations. So first case, let us take the easiest one. You know that b0 will come out to be 1. So that is the first expectation of psi 0 is equal to 1, which implies a0 to be equal to 1. This was the easiest one, right? Come to the second one. Second one is expectation of psi 1 is equal to 0, which implies expectation of, what is psi 1? b0 plus b1 x is equal to 0, which implies expectation of b0 is b0 plus b1 expectation of x, right? What is expectation of x? 0.5. Why? Because uniform in 0 to 1, the mean is a plus b by 2. So expectation of x is 0.5. So this is expectation of x, which we know is equal to 0.5 is equal to 0, which implies that b1 is equal to minus 2 b0, minus 0.5, minus 2 b0, right? Uniform. That you have to assume, otherwise, so here, right? X is from uniform. Otherwise, you cannot find out. It's a function of the distribution, right? Okay, I need one more equation. What is the equation? Expectation of psi I square is equal to 1, the orthonormal property. Psi I square is psi I psi j delta ij, so I equal to j, that one. So expectation of psi 1 square is equal to 1. Now what is expectation of x square in terms of variance? Variance of psi 1 minus expectation of psi 1 whole square. Variance of x is equal to e of x square minus e square of x. That negative sign take to the other side, you will get it. So this is equal to variance of psi 1 square. So that will become psi 1 plus expectation of psi 1 square is equal to 1. What is this term equal to? 0. Right? This term is equal to 0. So variance of psi 1 should be equal to 1. What is psi 1? Variance of psi 1. Psi 1 is equal to b naught plus b1 x is equal to 1, which implies variance of b naught is equal to 0, constant. Variance of b1 x is equal to b1 square. Variance of x. What is variance of x? Uniform b minus a whole square by 12. If a to b, b minus a whole square by 12 is the variance. So in this case, b minus a is 1. 1 square is 1 divided by 12. So this is equal to 1 by 12, which is equal to 1. So which implies b1 is equal to 2 root 3, 4 into 3r. And you can see I can you do the plus minus thing here itself, and that plus minus will ensure that I get that, as I said, it can be in both directions. So here itself it will be plus minus, right? 2 root 3. What is b naught? Minus root 3, right? So what is the polynomial then? Finally I get psi 0 is equal to 1. Psi 1 is equal to minus root 3, 1 minus 2x, right? Something like that. Yeah. Okay. And like that, you can imagine you can find out psi 2, psi 3, psi 4, all of those using this properties, you can continue to find it out. Okay. And you can do it sequentially. By the way, that root 3 is the normalizing factor. If you remove root 3, you can remove the negative sign also. So 1 minus 2x is what you will get. That's an orthogonal polynomial. Okay. So that root 3 is coming because I am finding out orthonormal. If you search orthogonal polynomial for uniform in 0 to 1, you will see that they will give 1 minus 2x. That's constant they don't give. Orthogonal, not orthonormal. Okay. And generally in Wikipedia and many places they derive this for uniform in -1 to +1. I mean, the mean goes to 0, life becomes a little bit easier. I did it from 0 to 1, does not matter. It can be from A to B also. And depends, right? Whatever you are using. Okay, so you know how to find it out, but you also understand you are not going to use this for nth other polynomial, right? And you also know that for doing this, you need to evaluate this variance and expectation that I was evaluating, which is basically the inner product or an integration. And this integration in many cases, if it is Gaussian, you cannot do that integration. You know property, you can use it, but if it is mixture of Gaussian, and then you don't even probably know the property. So you will not be able to evaluate this always analytically. And so you will need quadrature rule or some rule for evaluating the integration, which we will talk in the next lecture. Okay. But coming back to here, can you think of any other way taking motivation from vector algebra for finding out this orthogonal basis? How do you find out orthogonal vectors? One way is Gram-Schmidt orthogonalization. where you assume vectors and then do the Gram-Schmidt transformation, and that converts those vectors into orthogonal vectors. You can read about it if you don't remember it or you have not learned it. Read about it. It will not take more than half an hour to learn that Gram-Schmidt transformation. Same thing you can do here. You can start with monomials like 1, x, x squared, x cube, and then transform it with Gram-Schmidt orthogonalization. And that can give you the same thing that I derived here. But you should not use Gram-Schmidt orthogonalization. It's very unstable. And because it's unstable, it is not used. So there are other ways of doing it. There is already a routine that you can see that is known as orthopol. So this routine can generate very efficiently different types of orthogonal polynomials. In fact, in the recent homework that I have uploaded last week, this orthopol has been given to you that you can use that. Okay, you can use that. The original implementation was in Fortran by a CS faculty from Purdue, 94, 95, Fortran 95, I think. And then Ilias Bilionis, who also happens to be our speaker in the seminar series we are having this Wednesday, he converted that into Python. So there is a Py orthopol also, which Ilias Bilionis wrote that code, so that you don't need to use Fortran because people are more comfortable with Python nowadays, right? So that's why. Okay, so that you can use to find it. What about multivariate case? Multivariate case also same thing can be used, same properties you will use, right, to find it out. In multivariable case, what will happen? This polynomial will be in x and y, or x1 and x2. The PDF will be of x1, x2. The same property you will use and find it out. Life will become hell, that's a different story, but in theory you can use it. If you are very lucky, what you will get, and that's what we mostly work with, is multivariate case, because multivariate you cannot avoid in reliability, but you first transform those multivariates so that they are independent. If they are independent, then life is easier. What you will do is that for each of the variable you will form the orthogonal polynomials and then do a tensor product. Okay, so for multivariate case where the variables are independent, we can find orthonormal or orthogonal polynomials for each one variable at a time, and then take a tensor product. What is tensor product? Each element of a vector should be multiplied with every other element of another vector. I mean, right? So if it is n vectors and n vectors, you will end up with n square, because each element will get multiplied with everything. So you'll end up with n square elements. So basically, this essentially means that you will first find out psi 0x, psi 1x, and that will be your set of basis for x, and let's say the other variable is y. So you will find out again this psi, let's call it 1, because these two may not be same, right? Form y, and then do a tensor product. You can imagine that if the variable is uniform, the first set of polynomials you will get is legendary polynomial. What I was deriving was legendary polynomial. If the variable is, let's say, Gaussian, you will get Hermite polynomial. So if one variable is uniform, other is Gaussian, the product will be product of legendary and Gaussian, and it will solve it out. And but this only you can do if they are independent. If you're dependent, then you have to do the complete derivation, which is non-trivial. You can solve it. So even for this, it is combination. So obviously, it will be exponentially grow. So that too will happen. That is not NP problem. That is NP hard. It is not called NP. That is what you are saying is NP hard. This is exponential growth. Both are, there is subtle difference between the two. Okay. Not every exponential hard you call it NP. NP hard has a different meaning. Okay, but it's a exponentially it will grow. Actually, it grows factorially. Okay. It grows factorially, not exponentially. And that I'll show next time. Most of the times we do that because otherwise formulating that becomes difficult. But if you can formulate that, you can use it. But most of the time we first convert the dependent to independent, then use it. We even prefer to convert all variables sometime into uniform, 0 to 1 or -1 to 1, and then use Legendre for every variable. Because you can always transform variables between 1 to 1. This was Legendre, what I derived. These two. The first two are Legendre, first two polynomial. Because I assume this is uniform. So whatever you get is Legendre in that case. Yes. Hermite. Okay. Those names are not important. You know how to derive it. I mean, if I don't say it is Legendre, how does it matter? You will still use this polynomial. Right. I mean, how does it matter? Anyways, so we'll stop here. Next lecture, we'll start with the quadrature. Okay. Thank you.